Welcome to this explainer. Today we're looking at something truly colossal, the hull of an FPSO. That stands for Floating Production, Storage, and Offloading Vessel. Now, I want to hook you immediately with this thought. An FPSO hull is not just a big ship. It is the absolute critical foundation of an entire floating oil field. Get the hull wrong and literally nothing else works. By the end of this explainer, you're going to understand the exact commercial drivers for choosing an FPSO, how its hull construction differs from a standard trading tanker, the high-stakes decision between a conversion versus a new build, the life-saving principles of risk-based topside layouts, and the key SOLAS regulations that govern the whole shebang. So let's dive right in. Here is our roadmap. We'll be covering the commercial advantage, the engineering leap from a standard tanker to a floating field, the choice to convert or build, risk-based layouts, and finally, navigating those strict SOLAS rules. Let's jump straight into Chapter 1, the commercial advantage. We really need to ask the fundamental question of why an energy company would choose an FPSO in the first place. I mean, seriously, why put a multi-billion-dollar oil field on a moving ship? Think about the sheer logistical madness of this concept for a second. You've got a highly volatile, massively heavy, incredibly complex processing plant. Why wouldn't you just build a stable, fixed platform bolted securely to the seafloor? Why choose a floating vessel that rolls, pitches, and heaves with the ocean waves? Well, the crucial point here is that FPSOs absolutely dominate in places where fixed platforms simply fail or just aren't economically viable. There are three main scenarios where they really shine. First up, marginal fields. This is where the reservoir is just too small to justify the massive upfront expense of a fixed platform and a massive pipeline network. Second, isolated fields that are way out there, far away from any existing infrastructure. And third, ultra-deepwater fields. We're talking water depths over 1,000 meters, where building a fixed platform down to the seabed is basically technically impossible. But here is their ultimate commercial superpower: high redeployment value. Unlike a fixed platform that has to be completely decommissioned right where it sits, an FPSO can simply disconnect its moorings and move to a completely new field when the oil runs out. That flexibility is a huge financial advantage. Moving right along to Chapter 2, we know why we want an FPSO, but how exactly are these standard global shipping tankers transformed into specialized oil processing leviathans? Notice the sheer scale of these structures. The base hull of an FPSO is almost always derived from a really large oil tanker design. Builders rely on proven, class-approved designs like Aframax, Suezmax, or those massive VLCCs, very large crude carriers. We are talking about hulls capable of carrying up to 300,000 deadweight tons. They use these tanker hulls because their structural properties are incredibly well understood, and there's already a mature, cost-competitive global supply chain ready to produce them. The hull's primary job, besides keeping everything floating, is massive cargo capacity. To put that into perspective, it typically holds between 1 to 2 million barrels of crude oil at any given time. If you look inside that massive hull, you'll notice this internal grid arrangement. You have cargo tanks arranged athwart ships, which is just a maritime way of saying side by side across the beam. Flanking these cargo tanks are wing tanks, which are typically used for ballast water to keep the ship stable. Below all of that is a double bottom, also for ballast, which acts as the primary physical defense against grounding. This structural subdivision is absolutely essential for managing the constantly changing weight as oil is processed, stored, and eventually offloaded. But remember, an FPSO isn't just a giant storage tank. It's a floating factory. And that factory sits right on the deck in what are called process area units, or PAUs. These are self-contained processing modules built entirely onshore and then lifted onto the deck as complete packages. Now, look closely at how they sit. They don't just rest flat on the deck. They're actually mounted on elevated structural stools. This is honestly absolute genius. Sure, it provides clearance for pipes and maintenance, but way more importantly, it provides vapor clearance. Hydrocarbon gases are heavier than air. If they leak, these elevated stools allow the dangerous explosive gases to drain away safely and disperse over the sides, rather than pooling dangerously underneath all that hot equipment. All right, this brings us to Chapter 3, and honestly, the highest stakes decision in the entire project lifecycle for the developers. Do you convert an aging tanker, or do you bite the bullet and commission a brand new build? Let's contrast these two paths because it's a tough call. Converting an existing tanker is seductive. It's fast, maybe 18 to 24 months, and it's definitely way cheaper up front. But there's a catch. An older hull carries accumulated fatigue damage from years of bashing through ocean waves. When you permanently moor it as an FPSO, that continuous cyclic wave loading can actually accelerate crack propagation in old welds. On the other hand, a new build is slow. We're talking 36 to 48 months, and it comes with a massive upfront cost. However, it gives you a 25 to 30-year design life with absolutely zero fatigue uncertainty. You get exactly what you need from day one. So how in the world do they decide? I want to give you a really sticky, memorable rule of thumb: 100,000 barrels per day. If your project lifespan exceeds 15 years and your production hits or exceeds this massive number of 100,000 barrels per day, a new build is almost universally the right choice. The topsides weight and the sheer process complexity at that massive scale strictly demand a purpose-designed hull to ensure structural integrity and overall safety. Okay, let's shift gears and move to our fourth section: risk-based deck layout. We're moving the narrative from the steel beneath the water up to the topside deck. And I really want you to view this not just as a standard engineering diagram, but as a deliberate, high-stakes survival plan. Looking closely at the top-down spatial layout, you'll see that every single piece of equipment is placed following one fundamental rule of hazard mitigation: put the most hazardous equipment as physically far away from the human crew as possible. It's deliberate hazard separation, engineered from the ground up to keep people alive if the absolute worst happens. Let's walk through this layout chronologically, moving from the safest areas to the most dangerous. Number 1, right at the stern, you have the accommodation block, the living quarters. Crucially, this is positioned upwind of the prevailing winds. Number 2, moving forward, you hit the low-risk utilities like power generation and water treatment. Number 3, we enter the process modules where the oil, gas, and water are actually separated. Number 4, things get really serious with the high-risk compression modules where gas is pressurized to extreme levels. And finally, number 5, at the extreme bow, downwind of literally everything else, is the flare stack and the turret mooring. If gas leaks, the wind blows it entirely away from the crew. It's brilliantly simple, yet incredibly effective. Entering our final chapter, navigating SOLAS rules. We need to explore the international legal frameworks that basically force these floating factories to operate with the exact same safety standards as global shipping. SOLAS stands for the Safety of Life at Sea Convention. It is the fundamental international maritime safety treaty. Now you might be wondering, wait, it's an oil platform. Does maritime law even apply? Absolutely yes. Because an FSPO is legally classified as a ship under the International Maritime Organization framework, SOLAS compliance is completely mandatory. It is not optional. The hull is a ship, and therefore it must follow the strict rules of a ship. So what does SOLAS actually demand? Well, some of these rules are actually fascinating. For instance, ballast tanks must be painted with light-colored paint. Why? Well, because it makes structural inspections for tiny cracks and rust way easier in the dark. SOLAS also dictates strict watertight subdivision through bulkheads, and, most importantly, damage stability. The naval architects must mathematically prove that the FPSO will remain afloat and stable, even in a worst-case scenario. Like what happens if 2 adjacent compartments are violently breached and flooded completely open to the sea? It still has to float. Because of these incredibly strict regulations, naval architects must rigorously map out invisible hazards all across the vessel. Look at what's called Zone 0. This is an area where an explosive atmosphere is continuously present, like the airspace directly inside the cargo tanks, just hovering above the crude oil. Extreme explosive risks in these specific zones demand specialized venting, intrinsically safe electrical equipment, and incredibly strict access controls. Safety dictates literally every single inch of the design. So the crucial point we've learned today is that getting the hull right, the commercial logic behind it, the structural integrity, the risk-based layout, and that stringent SOLAS compliance is really just the foundation. The hull simply sets the stage. But it leaves us with a massive cliffhanger. How in the world do you physically transfer high-pressure oil and gas from a stationary wellhead miles down on the deep seabed all the way up into a massive ship that is constantly rolling and spinning in the wind and waves? That is a wild engineering puzzle, and it's exactly what we'll uncover in our next explainer on gathering systems. Until then, stay curious.